Okay, so today's online lecture is Tuesday, March the 17th. Happy St. Patrick's Day. Hopefully you are wearing green. See if I can draw this nice little four-leaf clover. And at some point, maybe you'll find a pot of gold at the end of the rainbow. I don't think this is, okay, too much fun. All right. Today we are going to just review some amines. We're going to review the amines. I've set my timer for 20 minutes, so hopefully we'll keep to that. So we're going to review the amines. I'm going to do an acid-base reaction. We're also going to do the mechanism for the Hoffman, because you're going to have to do the Hoffman elimination mechanism for your quizam on Thursday. And then I'm going to provide you some questions that you can add to yesterday's questions. And then once at the end of this week, by Friday, you can submit it by email, and you can just write that as Chemistry 314, and this is your online POCL, and then your name. And I need first and last name. Remember, this for this whole week, it'll be worth 5 points. Now, tomorrow we'll actually do a synthesis question and answer your questions. If you have any review questions, if you have questions you want me just to do for tomorrow, put them in the discussion board, and then I'll put them in this YouTube video. Okay, so first let's just review acid-base chemistry. So we have benzoic acid and we have an amine. Now we know that amines are our organic bases, so this is our base, and then carboxylic acids are our acids. So this should make it easy to recognize that this is your acid and this is your base, and your base will take its lone pairs and abstract that hydrogen, and those electrons will go with that hydrogen, and then your product becomes the benzoic acid, the benzoate, with losing its hydrogen, so that's its conjugate base, and then your nitrogen has taken that hydrogen, and that becomes your conjugate acid. Remember, pKa's go with acids. The pKa of a carboxylic acid is between 4 and 5. The pKa of your conjugate acid is going to be, do you remember this? This is 11. So which way does it go? It goes to the higher pKa value. So 5 minus 11 is like 6 zeros. So it's about a million times to the right. Now, pKa values are the protonated. So if you have a protonated ammonium without any alkyl groups, that's a pKa of 9. Remember, we said they were opposite, they were odds. If you have something like an aromatic, like aniline, that pKa was like 5. And if you have any kind of aliphatic, these electron donating groups, we said that that's going to be a pKa of 11. So you know you're going to have to rank your acids and bases. And so the most basic is your aliphatic amine. So that would be your amine here is your most basic. And then your second would be without the electron donating group. So it'd be just the NH3. Okay, so this is number 2. And then your third would be the aromatic amine. So this is your least basic amine. And so if you do not have it protonated. So it's just that free base. They call it a free base. Okay, the free base without the protonation, pKb values. You can look at pKb values. That's the base. And that's a 9. The pKb value for the ammonia is a 5. And the pKb value for the aliphatic is a 3. So 3, 5, and 9. We're still dealing with odd numbers here. So hopefully that gives you some kind of feel. Now, there is a reaction I wanted to talk to you about, and we're going to be talking about peptides. So I'm going to give you a new reaction because you know I like not to just to do review, but this makes peptide bonds. And I think we might have someone in our group making a peptide bond. And a peptide bond is an amide bond, and it's in the proteins. And we'll be talking about that in April. But there's a special reagent called DCC. This is dicyclohexyl carbo diamide. What does that look like? Dicyclohexyl. This is a cyclohexyl, and this is an imide, new functional group. And you can see that you have, oh no, that's saturated. Okay, so that's your dicyclohexyl carbo diamide. So this is a diamide. So you see that's a diamide. And what this does is it will absorb a molecule of water, right? H2O. And the carbon becomes a carbonyl. And the nitrogens each get a hydrogen. And then they still have their cyclohexyl. So that's a dehydrating reagent. Dehydrating reagents take away water, one molecule of water. And this is actually a new functional group called a urea. It's the first functional group ever synthesized by organic chemists. Yes, that is the structure of urine, and this is a urea. Very stable molecule. Okay, so this is a carbodiamide. And what I want to show you here is you can use this reagent with a carbocylic acid. So let's just take benzoic acid. So you can take a carbocylic acid, and then you can just take some kind of regular amine. Now, I've told you that you would have to convert so our plan to make an amide bond. So how would you make an amide bond? Well, you know in the ranking of your carboxylic acid derivatives, you have the acid chloride first, right? This is the top. And then your acid anhydride. And then you have your ester. And then you have your amide. And then you have your carboxylic acid. So how do you go from a carboxylic acid to an amide? Now you know that you could convert this to an acid chloride and then go down to the amide, right? So you would throw in some thionyl chloride and then you'd throw in some pyridine with this amine here, and voila, you would have your amide. Okay, well, you can also use this DCC reagent. And so this is how protein chemists make proteins. Okay. And so if you throw in the dicyclohexyl carbodiamide, it will form, and you don't have to know the mechanism, but it will form an activated ester. So this oxygen here will bond to this carbon, and then this nitrogen here will take away that hydrogen. Okay, I keep the colors here, and then you have this nitrogen here. It's like, oh, Shouldn't be a benzyl in there. Just a straight one. Okay. And so this is an activated ester, and we talked about that yesterday with the thionyl chloride. And so this is, when you say an activated ester, this is an excellent leaving group. Okay, and so once that's an excellent leaving group, now this amine, that's a weak nucleophile, can come in here, those electrons go up, they come down, and then they leave. And when they leave, it also takes that hydrogen here and makes the urea. So you end up making your see, there's your amide, and then you get also your urea. And I know some people are going to be doing this in lab, so you will have a chance to see their poster. So this side here will end up taking that nitrogen, will bond with one of these hydrogens, and you get urea. And then what's really nice about this is this is water soluble. So you can basically put that in your separatory funnel and you can get your amide out clean. Okay, so that is just a little information there. Back to just a little bit of review here. You need to be able to do this mechanism. So what is this mechanism? To go from there, see, likely you would be given the reagents here. So let me give you the reagents. Let's do excess iodomethane. And then we're going to add silver oxide, water, and heat. All right, so you can do the heat third. So since you need to know this mechanism, the first thing you want to do is exhaustive alkylation. And we know that that is an SN2 reaction. So you get CH3, hydrogen, and then you keep doing that and keep doing that, and you can just go ahead and draw in your quaternary ammonium salt. And you know this is a great leaving group. And it's a bulky leaving group. So that makes it, that's why you're going to get a Hoffman. Now what's the counter ion here? With the silver oxide and water, the counter ion becomes O-. And we know that's a strong base. Now, this is your alpha carbon with your leaving group, your bulky leaving group. And these are your beta hydrogens. This has 3 hydrogens on it, and this is your beta here with 1. And normally you get your more substituted elimination, but in this case you get your least substituted, and that would be your Hoffman product. So if we go ahead and draw that elimination product, and you see how I have 3 electron flow arrows. And I will trace them again because you will be required to draw your 3 electron flow arrows. So here, the OH base will take its lone pair and take a beta hydrogen. That's 1. Those electrons then go towards the alpha carbon, and then the leaving group on the alpha carbon gives you your Hoffman alkene. Okay, so be sure to be able to do that mechanism on your quiz exam on Thursday. The other two reactions I would like to go over, and then we will work on, I'll give you your questions that you can turn in for your POGIL this week. Okay, so proposed starting material and reagents for this compound here. And also for this compound here. The first thing you want to do, of course, right here is look and see that this is a primary amine. So you're thinking Gabriel synthesis, right? And so in Gabriel synthesis, you know that you need this phthalimide salt. And we'll just go ahead and make it the potassium phthalimide that you could purchase. And you know that's going to be your first reagent. And what is that going to react with? Well, it's going to react with this whole group here because the nitrogen is coming from the phthalimide. So if we want to draw that group, and this needs to be a primary leaving group. So this could be, we got 2 carbons here, 1, 2, and it could be an alkyl halide, or it could be something like a tolusyl chloride. So if you had an alcohol, you could make it a tolylate. Those are excellent leaving groups too. And then the second reagent you would need, so what was your intermediate there? Your intermediate would be 1, 2, and then the phthalimide, right? And then you'd have to release this, so that's where you would need second hydrazine. So, and heat, and then that would release your product. And so this would go to there. And that's a Gabriel synthesis. All right, so the other one here, this amine, so what is it? It's an amine, and the nitrogen is bonded to 2 carbons, so it's a secondary amine. So I would like to make this from a aldehyde. So let's make this an aldehyde. 1, 2. So what are we going to do? What's the reaction? Reductive amination. Remember, ketones and aldehydes react with amines to do reductive amination. So then this side here would be NH2. All right, so there's your amine. Now what does that look like? Well, when they come together, we're going to lose water and we're going to make an amine. So we will have this here, and then the nitrogen comes here, forms the carbon-carbon double bond. And so that's the first thing you do. You just react it with this amine and this aldehyde. And then the second thing you do, you have to use like something like a mild reducing agent, sodium cyanoborohydride, and that will reduce the amine to the amine. And so that is a secondary amine. And you can make tertiary amines. This is pretty much the way you would do it. Okay, so now for your questions that you will need to work and turn in. All right, so this is your question. Fill in the boxes. So this is, what's the name of this reaction? What's the name of this starting material? Okay, so what's the name of the starting material? And then we're going to add CH3NH2, methylamine, and then we're going to throw in some sodium cyanoborohydride. And your job is then to tell me what that structure A is. Okay? And then we're going to add 1 CH3 iodide excess. And then the second reagent will be silver oxide and water. And the third will be heat. And so what is that structure B? And then we're going to add BH3THF, boron, and sodium hydroxide, and H2O2. What is that structure? C. Then, what are the reagents for D? Reagents for D to make this compound here, 1, 2, 3, 4, 5, the nitrile. All right. So what do you make there? And then, so reagents D, and then I want you to add dibal. And what is this product? E. All right. And then I want you to name that. I want you to name your starting material, and I want you to name your product. All right. We'll talk